Our next speaker is Arvind Neelakantan. Arvind is a research lead and manager at OpenAI, working on deep learning research for real-world applications. He got his PhD from UMass Amherst, where he was also a Google PhD fellow. His work was received Best Paper Awards at the NeurIPS and at Automated Knowledge Base Construction Workshop. And now, over to Arvind.
Hey everyone, I'm Arvind from OpenAI. I'm going to talk about text and code embeddings. This is work I did with many of my colleagues at OpenAI. We launched OpenAI API 2 years back, and it was powered by the GPT models. And the main use case was on like text generation, and it was a general purpose text generation model that can be applied to a lot of downstream tasks. So with GPT-3, our language model powering the API, one could do a lot of text generation tasks, as I mentioned before. And one more set of tasks that we were able to unlock was few-shot learning, where you give it few examples of input and output pairs, and the model picks up the pattern and can solve the task you described. So generative models at a high level, typically work by maximizing the likelihood. They can generate realistic content. They're useful for lots and lots of downstream tasks. One problem, though, is that they're not explicitly optimized to produce a single vector or embedding of the input. And if you look at it, many applications benefit from having a single embedding for an input. Okay, so let's take search, for example. You want to search on a large collection of documents. Given a query, you want to do data visualization, where usually you want to do things like clustering and so on. All of these use cases require an embedding of an input. So it's like a condensed representation of the input that you can use as features for your downstream applications. Okay. Now we'll talk about a class of models, contrastive models, that are explicitly optimized to learn a single embedding of the input. So if you're familiar with it, there are models like CLIP that have shown a lot of success in learning visual embeddings for tasks like image recognition and so on. And these models are, again, for the purpose of this talk, we will focus on contrastive models that are trained from large-scale internet data. And what we want to study here is, can we learn text and code embeddings via contrastive models that are really good? And by this, I mean, we want to have like a single unsupervised model that produces embeddings for a large set of tasks. And instead of like what is typically done in practice, where for every data set, for every domain, you have a separate embedding model. Okay, so let's start with what we mean by embeddings, right? It's a bit of an overloaded term in deep learning. Again, here, what we mean by it is you're given some input and you have an encoder neural network that produces a single vector for your input. Okay, and to train these kind of embedding models with contrastive loss, we use what is called as what is like paired data. Basically, you have two inputs that are related, and this kind of relation could mean things like it has the same sentiment, it talks about the same topic. In the case of CLIP, it's like there's an image and a text, and those are paired because the text is describing what's there in the image. Okay, so you have paired data, and then you have your embedding encoder model that produces a vector for both sides of the input. So you have the input from the both sides. Those are you run a few layers of your neural net, and then you get a single embedding for both sides of the input. Okay. And then the similarity function between the two inputs is given by cosine similarity between these two vectors. So this is like the high-level setup of the model. And once you have the model and the pair data, you need a loss function. And so what we do here is the pair data access the positive examples. So you want those scores between inputs in the same pair to be high. And with gradient descent, we usually do it with a mini batch, or stochastic gradient descent, we do it with a mini batch, and we're going to use the other examples in the batch as negatives. Okay, so the main purpose for that is computational efficiency. The positive examples in the other batch, you anyway need to do a forward pass and a backward pass on that. So we're going to reuse those examples in the other batch as negatives. So for every positive example, there are n minus 1 negatives, where n is the batch size, right? So you're kind of doing n square classification decisions of like, this is positive, this is negative. And yeah, that's it. So you have a model, you have pair data, and this is your loss function, and you can now train it. One important detail when training these contrastive models is that since the batch size effectively controls the number of negatives, increasing the batch size means there's more chances of having hard negatives in your batch. And having hard negatives means the model learns better features, right? So here's a simple experiment on a text search task where the metric is measured with mean reciprocal rank. Higher is better. It basically roughly tries to capture where the correct document is placed in, let's say, the top K documents provided by the model. Cool. So here you can see by increasing the batch size by 10 times, our performance goes up quite a lot. And this is just a small experiment. We'll talk more about experiments later in this talk, but this is to give an intuition of like the batch size is super, super important. And a lot of our work was on like how to efficiently increase our batch size. Cool. So we started off with contrastive models, went a bit more into the details of the model, architecture, data, and loss function. Now I'll give you the high-level recipe that we use to get text and code embeddings. Okay, the recipe is as follows. It's you collect pair data, and then you train with sufficiently large batch size. And turns out you had to do one more thing, which is the contrastive loss on its own is not sufficient to get very good features, and it's like better if you initialize with a pre-trained model. But that's about it. It's basically these three steps: initialize with a pre-trained model, collect pair data, and train with sufficiently large batch size. So this simple recipe, now you can apply that for getting text and code embedding models. So for text, we initialize with GPT, the text generation model. We collect unsupervised pair data, which is text pairs. These are neighboring text pairs in the internet. And then we train with a very large batch size. For code, we initialize with Codex, which is OpenAI's code generation model. We collect comment and code pairs. So this is like the textual comment in let's say in a function block, and then the code is the whole function. So we get this pair data of text and code, and then we train with a very large batch size. So by doing this quite simple high-level recipe, we can get these text and code embedding models. And this is quite different from how other embedding models work, where usually you pick a particular data, particular data set, particular domain, and you try to get very good embeddings for a particular task. And here what we're trying to say is we'll just collect lots of unsupervised pair data, and we'll train single models that as I'll show work very well on a large collection of tasks. Cool. So that's the machine learning research part of the model architecture, data set, loss, how we train it, and so on. And along with the research results, we also put out an API in the OpenAI API. So there's an embeddings endpoint that has been actually been around for more than 6 months now, and it's been used quite widely. So here you can just pass in an input text or code, and you get back a vector of numbers, basically, that capture the information about that input. And embeddings are useful for many tasks. So you could do things like data visualization. You can use them as features in regression or classification tasks. You can do zero-shot classification, which is one of the cool things that came out from our models, where even without like annotating data for your particular task, you can start getting pretty good classification performance. And then more downstream tasks like cold start recommendation, where you're trying to match a text, let's say a textual description of a product with like user information. And finally, another task that is like quite popular is search. So you have like large collections of documents or large collection of code pieces. You can like embed all that, build a vector index, and then query it quickly. So these are some of the use cases. And if you go to our webpage, you can like get a simple tutorial followed by code on how to do these things. Great. So I'll now go back to telling you more about the performance of our models on lots and lots of academic tasks. So before we go into quantitative results, this is just like a simple illustration of what's possible with these models. So we took the Amazon fine dining review data set, and there are labels of like, this is positive, this is negative, this is neutral, and so on. So what we did was, while embedding, we didn't use the label at all. We just take the text, embed them, and then project them into 2 dimensions. And then after we do that, we color it based on the sentiment label. And you can see that the model has basically done unsupervised sentiment discovery, where it's like neatly kind of like said, oh, these are all about negative these all have negative sentiment, these text pieces have positive sentiment, and something's in the middle. And now I'll dive into one way, one actually very popular way, how embeddings are used. So you have like classification tasks, where you're given a text, and let's say you want to classify it into a topic, you want to classify it into a sentiment, and so on. So we took like 7 data sets that are academically well studied. We tried our embedding models on these data sets. So we have 4 classes of text embedding models. These are basically models that have high performance, usually have high latency. Like our Da Vinci model has the best performance, and it's like the biggest one and has more latency. And the ADA model has lower latency and cheaper, but also performs weaker than the Da Vinci models. So we have 4 model classes here. And on average performance on these 7 classification data sets, you can see that our Da Vinci model performs much better than previous methods, and largely due to just unsupervised training. And the next set of tasks I want to go over is text search. Here, you're given a collection of documents, and given a natural language query, you want to pick out the document that's closest to that query. Okay, from the provided collection, and how it typically works is you offline embed all the documents, you build a vector index, and then at test time you query to get the closest document. And again, we see our Da Vinci model doing much better than previous methods. And one thing I want you all to um, take note here is, for the classification, it was a completely, the previous best method was a completely different model. They didn't care about search at all. And then vice versa for search, it's a completely different model that does very well on search, which was the previous state of the art. Um, and for us, we were able to get closer to having single unsupervised models to do well on all these tasks. And finally, I want to talk about code search. So here, given a natural language query and a collection of code blocks, you want to pull out the most relevant code given the query. Okay. So this is on 6 different programming languages, and we use the same model for all of that. And you can see that our models are perform much better than previous state of the art methods. And this is a task where we do exceptionally well compared to previous methods. Cool. So I want to drive the point again of we basically have a single model that just works very well on a wide variety of tasks, and it's an indicator that the model is robust. It's like if you take most embedding models outside, they're usually optimized for a single academic data sets, and when you try to apply them to real world settings, you'll find that they're often brittle. And and I think you know having your models depend a lot more on unsupervised learning. And if they do well on a large set of tasks, I think it's like you start getting signals of that this being a lot more robust. And to basically give you more, more points, more indications on our model being more robust, we have customers who are using our embeddings in real world tasks. And first, I'll talk about Fabius, which is a search enterprise search company that was using keyword search before switching to OpenAI embeddings. And as you can see in the text from them, it basically has our embeddings are just a lot more, lot better, and they're able to pull out more more data because it's not dependent on keywords, and since it's a semantic search, it can pull out things from thematic similarity. Next is Viable, which uses our embeddings for clustering. Here, their goal is they have their customers upload a lot of CRM data, and they want to present fine-grained information back to their customers. So this involves this is a cluster of people liking the product for this reason. This is a cluster of people who don't like it for this reason, and so on. So they use our endpoint to get the embeddings and then do clustering on top of them, and they get a big boost in clustering accuracy. And this is one of the cases where their clusters are also used in other automatic downstream tasks. And once you have a model that gives a big improvement upstream, it leads to kind of big improvements in many downstream tasks. And the final task I want to talk about is zero-shot classification. So FineTune Learning is an edtech company that is used that is used by children. And here they wanted a solution where if you have incoming video or text educational material, they want to automatically tag them into specific categories, right? And this set of categories are always changing and are dynamic. So you want a solution that can work zero shot. They were using other embedding methods like sentence bird beforehand. And they started using our embedding endpoints to do the matching and got much better results. Especially like if you can show like multiple categories, the embedding endpoint catches up with human experts, which makes their application a lot more usable. Cool. So yeah, we talked about text and code embeddings. There's a research paper and also an API endpoint. These models are being used in the real world, and they're applicable for lots of tasks. So if you're interested, sign up for the API and start using them. Thank you.